friends, my name is Mridul and I'm a faculty of electrical engineering and I teach electrical machines for GATE. Okay. So today we are going to talk on a topic which is transformers, and this particular topic has a very high weightage in GATE. Okay. The marks that you can expect from this topic is around 5 marks. Okay. So from transformers. Now today what we are going to discuss is a very important concept of transformers, which is basically the induced EMF and the current in a transformer. Now we all know that the induced EMF is due to the Faraday's law. Okay, so I will not be basically going into the working principle of transformer. Rather, what I am going to discuss here is about the behavior of the current as well as induced EMF. Okay, if you are not clear about the basics of or the working principle of transformer, you can go to the other videos where I have discussed the working principle of transformer. Here I will be focusing on the direction, rather, okay, instantaneous directions of the induced EMF with respect to flux, as well as the direction of currents and the reason of rise of current in primary when we connect a load. Okay, so I'll start from very basics. That is, we know that whenever we connect a load to the secondary, the primary current rises. Okay, so the thing is, we all know it, but the reason is why. Okay, so that is what we will be understanding here. We'll start from that point, and then gradually I'll go to the direction of induced EMF. Now, what I mean by direction of induced EMF is, we know that this induced EMF can be expressed by Faraday's and Lenz's law, that is, E is equal to rate of change of flux linking this particular coil. If this is E2, then it will be d phi by dt multiplied by number of turns N2. Say N2 is the number of turns of this coil of the secondary. Now, this is the magnitude of this induced EMF. Now, this is an AC component, right? That means every half cycle, the direction is going to change. Now, if I want to know what is the direction of the induced EMF at a particular instant, if I know the direction of the flux, say the flux is at a particular instant, the flux is flowing in this way and it is increasing. So what is going to the direction of this induced EMF? Whether it will be plus here or plus here. Whether the current will flow in this way or the current will flow in this way. So this is what the understanding is. And on this understanding, there is a GATE question in 2008 which we will solve after the explanation. Okay. So you see, the Lenz's law gives the idea of the direction of the induced EMF. So we put a negative sign here. But if we put a negative sign also, it doesn't clearly tells us that at a particular instant this will be plus or minus. So this is not really helpful for us. So we will be using the Lenz's law in a different way. Okay, definitely I will be using the Lenz's law, but not in this way. This is not giving, this formula or this expression is not giving us a clear-cut understanding of the instantaneous direction of induced EMF. Now what is Lenz's law? Now Lenz's law says that effect opposes cause. Now this is something which we will discuss. Okay, so these are the two topics that I am going to discuss: direction of the current, the reason of the current, and induced EMF directions. Okay, so let's start with current. Now you see, what happens in a transformer generally is we connect a AC source in the primary. So primary current starts flowing. Okay, and if the load is open circuit, I mean the secondary is open circuit, there will be no load current here, right? So once we connect this secondary to a load, then secondary current flows, and due to the secondary current, the primary current also increases. It increases by some amount. We know that I1N1 is equal to I2N2 and those things. So here you will be understanding why you use this formula and from where this concept is coming. Okay, this is very important. So now let me explain. So first of all, you say primary current we'll have two parts. One is no load and one is load current. Load component, or let us say just name the components, that is load component. And now no load current also has two components. One is core loss component and one is magnetizing current component. I'm not drawing the phasor of this. Let me first explain the topic, then I will draw the phasor and we will also see what is phasor. Okay. So first of all, when the load is not connected, it is called, the component that will be flowing is called no load current. Now, this no load current, okay, I'm not going to going inside the concept why no load current is flowing and why not. Just I will tell that there will be some no load current, and the reason is there will be some core loss component and there will be some magnetizing current to produce the flux, right? And I'll show you the phasor of this. Now suppose this is my supply voltage V, and say this is this supply voltage Vs. Okay. So generally what happens is, let us say it's a nearly ideal transformer case. So in nearly ideal transformer case, generally what will happen is, means I am neglecting the leakage as well as the resistance of the coil. Okay. So if I neglect the leakage component and the resistance of the coil, then what will happen is the flux that will be produced will lag the supply voltage by 90 degrees. This is what it happens. Now, in this case, what will happen is there will be two current components of no load. That is, first one is the core loss component. Now, the core loss component will be along the supply voltage Vs. Why? Because whenever we say loss, now this loss means real power, and real power means the power factor is unity. Or in other words, the angle between the IC component or core loss component and the source voltage should be 0. Okay? And then comes the magnetizing current component. So this current component is responsible for creating this flux, and this will be along the flux. It's like an inductor current, right? If you connect a purely inductive pure inductor across a AC source, then the current that will be flowing will be 90 degree lagging from the source, right? And the phase or the flux will be in phase with the magnetizing current. So this is something which I expect that you know. I'm not going into what is core loss. That will be a different topic again. Okay, and what is magnetizing current, why, and this all relation between flux and magnetizing current. Those topics I have already explained in the previous videos. Here what I'm going to explain is, suppose I have a no load current, and this current will be the addition of these two current. In phasor addition, suppose this is my I naught. So this is my no load component. We all know. Now we also know that this no load component is very, very small. It will be in milliamps. So I naught magnitude will be almost in microampere to milliampere at max. Very, very small. So now this is the no load current, what is going on. Now the moment we connect this switch, that means we connect this load to the secondary. Then what happens? Then we know that the primary current, this was the primary current I1 at the time of no load. The moment we connect the load, this is no load. The moment we connect the load, this primary current increases. Why? This is something which I am going to explain. Now, how much it increases? what happens is generally this I1, I have already a no load component that is I0, and with this one more component comes, which I will say I2 dash. That means this component is increasing due to the secondary current I2. Now this is the secondary current, and this is a current which is increasing in the primary. Now there is some relation between these two. What is the relation? From where the relation is coming? This is what I am explaining. I hope you are following me. Okay. Now you see what happens is, we all know that I1 N1 is equal to I2 N2. Now from where it's coming? This is coming from this particular equation. Now what happens is, okay, I will come to this after some times. So from where this expression is coming, I will come after some times. Now what I will do is, I'll explain that why this is increasing, why this component is coming when I am connecting the secondary. Okay. So see, what happens is, suppose my supply is Vs. Okay. And if I am considering that Vs is almost equal to the induced EMF E1, magnitude is almost equal, because the loss that is here, or the voltage drop that is there in the coil due to some resistance and leakage, I have neglected them. Or even if it is there, it will be 1 volt or 2 volts, which is negligible. Okay. Now, this voltage, say it is RMS is fixed RMS. Okay, the RMS value of the supply, say 220 volt. Okay, that is constant. And the frequency is 50 Hertz, which is constant. So now induced EMF, I know it is equal to 4.44, this is RMS value, into frequency of the supply, okay, into phi m, okay, into number of turns. Since this is 1, so this is number of turns in the primary. Clear? We know these things. Now I can say that Vs is proportional to frequency into flux into number of turns. Now since the number of turns is also constant in the primary, frequency is constant, voltage is constant, so this is constant, see, this is constant, this is constant, this is constant. So what happens is, phi m is, I can say, should remain constant. That means the flux, RMS value of the flux is RMS value, right? Not instantaneous value. Remember this thing. These are all RMS quantities. So the RMS value of the flux flowing through the core should be constant. This is very important to understand. That means the flux that is required by the core for this particular supply is constant. Now you will think, what will happen if the flux is constant? What is the relation? This is what we will discuss here. Now suppose what we have understood is flux is constant. Okay, so what are the things that we have understood? First thing is, I1 will be equal to I0, no load component, plus a second component which is increasing due to load current or secondary current. And second thing what we have understood is, flux is proportional to V by F into number of turns N1, and if these three components are constant, so what happens is, this is constant. So flux is constant. Now, we know that flux is equal to MMF by reluctance. Or in other words, if the reluctance is constant, so what happens is, flux is proportional to MMF. Okay? So flux is proportional to MMF. Now, the moment I connect this secondary, then what happens is, by Lenz's law, what happens is, the induced EMF should oppose the change. Now, induced EMF, now what is the change? You see, this is where Lenz's law will be understanding the Lenz's law. Now, what Lenz's law says that effect opposes the cause. Now, what is the cause? The cause is the rate of change of the flux. See, the cause is not the flux. The cause is the change in the flux. If there is a constant flux here, then there will be no induced EMF. Induced EMF will only be there whenever we have change in flux. So the cause is the change in flux. So suppose the flux is increasing in this particular direction as it is shown. So if flux is increasing in this direction. So if flux is increasing in this direction, what will happen is the induced EMF direction will be such that the current produced in the secondary will be such that the flux produced due to the secondary current will oppose this flux. That means Lenz's law says that effect opposes cause. Okay, so here the effect is flux produced by induced EMF. This should oppose whom? The flux, magnetizing flux which is produced, or let me say this is the phi m1 and let me say this is phi m2. So the phi m1 that is produced by the primary will be opposed by a secondary flux which is produced by the induced EMF of the secondary. Now that means the induced EMF direction should be such at a particular instant that it will oppose the change in the primary flux. That means if primary flux is increasing in this direction, then the secondary flux that will be produced will be opposing. That means it will be in this direction. I hope I am clear. Now the thing is, what happens is the moment, I hope you understood this much. So now I will take further this discussion further, that what we have understood is the moment secondary current is connected, so what will happen is the flux, total flux in the core will be phi m1 minus phi m2, let us. Suppose at no load what was happening? Only primary flux was there. And that primary flux was, suppose this is the magnetizing flux phi m, so this was okay, constant. Now the moment I connect the secondary, there will be a secondary flux which is going to oppose the primary flux or the flux produced by the primary. Now due to this reason, what is happening is this flux reduces because it's opposite direction, right? And the thing is, this flux is constant, so it cannot reduce. So since it cannot reduce, what will happen? It is constant. So the thing is, this particular value should increase so that the ultimate value is constant. Okay? So now this phi m1 should increase so that it can interact, or it can balance the secondary flux, so that the difference is always constant. Okay? So by how much should this flux increase? Now this is a question is, okay, so what we understood is, since this is constant, so it should not decrease. So whenever secondary flux comes, this primary should increase. Now the thing is, by how much? So the concept is, the secondary will produce some MMF. And the primary should produce equal and opposite MMF. To balance, so the primary current will increase such, the quantity will be such that the MMF that is produced in the secondary will be balanced by the primary. Are you getting my point? So, I can say that the secondary MMF, what is the MMF that is created in the secondary? So, MMF produced in secondary, because I know that flux is proportional to MMF. So, if the MMF of the secondary is balanced by the MMF increment in primary, then my flux is balanced, flux is constant, everybody is happy. So, MMF in secondary, MMF we know is number of turns into current. So, in secondary the current is I2 and the number of turns in secondary is N2. Now, this should be balanced by the increment current, increase in the current in secondary. So, this should be equal to MMF in primary. So, what is the increment of the current? So, this is the part which is increasing in the primary. So, the current that is there in the primary I will write as I2 dash. And this is the component which is increasing in the primary. And this multiplied by number of turns in the primary. So, it is the actual formula is this. This is the actual formula. But now, you see what happens is, this I0 as I say, or no load current component is very, very small. So, what happens is, this magnitude, if you see, I1 magnitude is, the primary current I1 magnitude is almost equal to I2 dash. I am talking about magnitude, not about phase. So, the magnitude will be almost equal. Because this will be around say 20-30 amps and this is say 20-30 micro or milliamps. So, even if I add, the primary will be around 20-30 amps only. Okay. So, then since this is nothing but a magnitude, so now from here I can write that I1 N1 is almost equal to I2 N2. And hence the formula I1 N1 is equal to I2 N2. So I hope I'm able to explain the reason behind the increment of the primary current whenever a load is connected. Okay. Now I'll go to the next thing, which is direction of the induced. Okay. So the next topic, which is, so we all understood why the current is increasing. Now we'll talk about the direction of induced EMF. Now I have already explained that the direction of induced EMF at a particular instant will be such that the flux produced due to the secondary EMF or the induced EMF will be in such that it will oppose the increment of the primary flux. This is a little bit confusing. So what we'll do is we'll take a real-time example. For example, in 2008, 8 questions was asked on this particular concept. So we'll directly take that question and through that question I will be explaining. Okay. So the question says the core of a two-winding transformer is subjected to a magnetic flux variation as indicated in the figure. Okay. So I'll draw the figure for you. Okay. So these are the diagrams which is given in the question, figures which are given. So they're asking that the induced EMF ERS in the secondary winding as a function of time will be of the form. That means what they're asking is, if I say this is a time, and this is 1, 2 and 2.5. So what will be the induced EMF ERS? Okay, that means from 0 to 1 will ERS be positive or negative, and what is the value? So there are 4 options. I'm not drawing the options. You can find it in your in the PPT. You can see it. See the options. So directly we will try to solve it. Okay. So what we know is induced EMF magnitude we can easily find out that is that equal to number of turns into rate of change of flux. Now you see, generally we consider that the flux is sinusoidal, but here the flux is not sinusoidal. And it is given that the direction of the flux here is this. That means as the flux is increasing in this way, this is a positive direction, so this is the direction of the flux. So flux is increasing in this direction from 0 to 1. And we can easily see that this is a linear line. So we can write it in this way, and del change in flux, del change in t, since this is linear. So here we can see that number of turns is ERS. So I'm going to find ERS is 200, and this del phi is 0.12, and this is 1 second. Okay, 1 second. So this will give me 24 volts. So we know that ERS magnitude is 24 volts. Now the actual question is, if my flux is positive, in this particular direction it is increasing, so my ERS will be plus 24 or minus 24. This is the real question. Plus or minus. Now you see, for that one technique which I can show you is, which I have already explained, that direction of induced EMF can be found out by Lenz's law. And what Lenz's law says? What Lenz's law says? Lenz's law says that if I connect a load here, then, and suppose if I connect a switch and I connect it here, then the current that will be flowing due to this induced EMF will produce a flux, say secondary flux. And this secondary flux will be opposing the change in the primary flux. So now you see, the flux in the produced by the primary is this phi, and it is increasing in this direction. Okay, it is increasing in this direction. So the secondary, how should the secondary flux be? It should oppose the increment of the primary. That means it should be in this direction. And how will this be produced? This will be produced when we want a flux in the secondary in this direction, opposite direction. So this will happen whenever current will be flowing. We can apply right-hand curves and we can see when the current is flowing in this direction. Okay, so that means current is flowing in this direction. Now you see, if I see in this particular load, current is flowing from this direction to this direction. That means what? This is ERS. That means what? ERS is positive and negative. So only then current will be flowing in this way through the load. So I can say that from 0 to 1, when the flux is increasing, the induced EMF ERS has to be positive. That means it should be this. Okay. After that, from 1 to 2, you see the flux is constant. So if the flux is constant, there is no change in the flux, the induced EMF will be 0. After that, from 2 to 2.5, again the induced EMF magnitude, if we find out, it will be 200 into del phi is 0.12 and the time is 0.5, so we'll get 48 volts. Now this 48 volts will be plus 48 or minus 48, that we have to find out. Again, in this case, what is happening? Now you see the flux is decreasing. So the flux is decreasing in this direction. That means direction is this only. But the magnitude, the change is negative. It's having a negative slope. Okay? So what this secondary, by Lenz's law, the direction of induced EMF will be such that the secondary flux will oppose the change in the primary. Change in primary is now, it is reducing. So how will the secondary flux oppose it? It will oppose the change is decreasing. That means it will not let the primary to decrease. How will that happen? It will happen when the flux will try to increase the primary flux. Secondary flux will try to oppose the decrement. How will it oppose the decrement? By flowing in the same direction of the primary. Very simple. So primary is flowing in this way. Okay. So now let us understand the current direction. So if I want a secondary flux in down direction, so the current you see, current in this coil should be in this direction. Okay, this fingers will show the direction of the current. That means if I draw it here, current should be now in this direction. That means it should go inside from R and it should come out from S. That means now current is flowing in the load from S to R. That means if this is the load and this is ERS, this is R and this is S. So now current is flowing from this point to this point. That means current will flow from this point, higher potential to lower potential. That means now this is the higher potential, this is the lower potential. That means now ERS, generally ERS is like this. So now you see it's opposite. That means 48 volts will be negative. Okay. So this is the answer. So this is the answer. Very simple. Okay. So I hope I am able to explain it. Now there is one more thing. In some books, what happens is the direction of secondary coil is changed. Now you see, if the direction of the secondary coil is changed, the answer will be different. Now you see, whatever I have done is for this type of winding. If my secondary winding changes, that means if it is something like this. So I hope you are able to find the difference in both the cases. Here you see it is wounded in this way, whereas here it is wounded in, so if this is clockwise, this is anti-clockwise direction. Okay, now suppose this point is R and this point is S. So what will happen is, so this is case 1 and this is case B. So this is very interesting. You see what will happen is, so from 0 to 1, when the flux in the primary is in this direction and it is increasing, here the secondary will behave in such a way that it will have an opposing flux. So for creating a flux upward direction, current will be in this direction. So current in this direction means current is flowing from R to S. So if current and through the load, how is it flowing? Through the load, current is flowing in this direction. That means from S to R. That means this is positive, this is negative. That means ERS is negative. That means it will be minus 24 volt from 0 to 1. From 1 to 2, anyways, there is no induced EMF, so it is 0. And from 2 to 2.5, I need a flux in this direction, so the current should be along this, and that means here current will be flowing in this from R to S through the load. So this should be positive and this should be negative. So that means this is positive and this is negative. So you see, in some books, this question is printed with the secondary in this way. In some books, it is printed with the secondary in the opposite way. And this is going to change what is the option, what is the correct option. So please make sure you see the direction of the coil properly, and then you answer. Okay. So I hope you have enjoyed this particular topic, and I hope I was able to explain this properly. So with this, I end this topic. Thank you.